Before we begin, let's look at this cold pack. Instant cold packs are often used by athletes for treating bumps and bruises. We know that a cold pack is not pre-cooled. Then, how does it become cold without being refrigerated? A cold pack contains two pouches, one filled with water and the other filled with a chemical substance. When the pack is squeezed, the pouches break and the chemical substance dissolves in water. The chemical reaction in the pouch absorbs heat energy from the surrounding. The temperature of the surrounding decreases, causing the pouch to become cold. The amount of heat energy released or absorbed when 1 mole of a substance dissolves in a specified amount of solvent is known as enthalpy of solution. For example, the ions of an ionic compound, AB, are held together by electrostatic forces of attraction. When it is dissolved in a solvent, its ions leave their ordered positions on the crystal lattice. Certain amount of energy is required for conversion of an ionic compound to its ions. This energy is known as lattice enthalpy and is denoted by delta lattice H0. Slowly these ions start moving freely in the solution and start interacting with the solvent particles. When water is used as a solvent, the dissolving process is called as hydration. If any other solvent is used, then the process is known as solvation of ions. Energy change occurs in dissolving of AB ions in the solvent is known as enthalpy of hydration of ions and is represented as delta hydration H0. As dissolution proceeds, the ions leave their lattice site and get mixed with the solvent. This total energy change of the solution is known as enthalpy of solution and is represented by delta solution H0. Thus, we can conclude that the enthalpy of solution of ionic compound AB is the sum of change in lattice enthalpy and enthalpy of hydration of ions. Let's look at the terms hydration enthalpy and lattice enthalpy. Enthalpy of hydration, delta hydration H0 of an ion is the amount of energy released when a mole of the ion dissolves in a large amount of water, forming an infinite dilute solution in the process. Lattice enthalpy, delta lattice H0 of an ionic compound is the enthalpy change which occurs when 1 mole of an ionic compound dissociates into its ions in gaseous state. The lattice enthalpy of a compound depends on the size of its ions and the charge on them. A decrease in the size of an ion increases the lattice enthalpy. That is, the enthalpy becomes negative and the reaction becomes exothermic. This happens because small ions tend to be closer to each other and have a shorter distance of separation, which results in a larger attraction force between the ions. Thus, lattice energy increases, that is, it becomes more negative. Alternatively, an increase in charge also increases the lattice enthalpy. That is, it becomes more negative. This is because the attraction forces between ions increases as the charge increases. It is not possible to determine lattice enthalpy through an experiment. But the same can be calculated by constructing an enthalpy diagram known as von Haber cycle. Let's look at an example. We know that the enthalpy change involved in the formation of a compound is called the enthalpy of formation. In this example, the enthalpy formation of sodium chloride from sodium in solid state and chlorine in gaseous state is minus 411 kilojoules per mole. Now, let's illustrate the different steps involved in the formation of sodium chloride. First, solid sodium changes to gaseous sodium atoms. The enthalpy change involved in this step is known as enthalpy of sublimation, and its value is plus 108.4 kilojoules per mole. In the next step, gaseous sodium atoms are ionized to form sodium plus 1 ions. The enthalpy change involved in this step is called ionization enthalpy, and its value is plus 496 kilojoules per mole. Similarly, the dissociation of chlorine takes place, and the enthalpy of dissociation is plus 121 kilojoules per mole. This is followed by chlorine atoms changing into chloride ions. Chlorine gains an electron, and the electron gain enthalpy is minus 348.6 kilojoules per mole. Finally, the gaseous ions combine to form solid sodium chloride. The enthalpy change involved at this step is known as lattice enthalpy. Let's apply Hess law to determine the lattice enthalpy released in this step. Hess law states that the enthalpy of change in a particular reaction is the same whether the reaction takes place in one step or in number of steps. Thus, enthalpy of formation equals enthalpy of sublimation of sodium plus enthalpy of dissociation of chlorine plus enthalpy of ionization of sodium plus electron gain enthalpy of chlorine plus lattice enthalpy. On substituting the values of all the enthalpies, we get the value of lattice enthalpy as minus 788 kilojoules per mole.